Welcome to another session with Smart Buildings Academy. Today, I'm going to talk about BACnet MSTP. I'm filling in for Phil Zito, who's traveling this week, and I welcome you to the show. Um, I asked myself at first, who should my target audience actually be for this broadcast? And I remember back in the days when BACnet was first becoming a big deal, and there wasn't a whole lot of training available. So this session is geared mostly for people who are new in the building automation field, who are struggling with understanding what is MSTP and what's the big deal about it. So if you're starting out and need more information, hopefully this session will help you understand a little more about BACnet MSTP. So the first thing I'm going to do is cover what is BACnet MSTP. So it's a subset of the BACnet communication protocol, and it's specifically designed for master-slave token passing MSTP networks. It's used for local, low-speed networks and building automation systems, and it allows for different devices to communicate with each other. And unlike other BACnet network types that use different forms of communication, MSTP uses a serial communication method. And that's what it looks like. When you say serial communication method, in this case, the definition of serial communication is pretty much exactly the way the physical bus topology looks. It is a system wired in parallel, and the communication goes from one device to the next device to the next device to the next device. So let's look at the object, the OSI layers. Here we have the physical layer, the data link layer, the network layer, and the application layer. And this is the OSI layer. BACnet layers are very similar. So we're going to be focusing on the MSTP level, but let me define for you real quick what these layers are. The physical layer is the media used to communicate over RS-485. The data link layer is the subnet communication. For example, the communication of MSTP on a field bus. That's this guy. The network layer is typically where your supervisory devices are, and that's where IP messages exist and route outside of the local subnet. The transport layer, this is where data verification exists for communication. Typically, when you're transferring code or you're logging into the system, the verification of the transport is made at the transport layer. The session layer, this is where the conversation is initiated. Oftentimes, two supervisory devices will create a session to discuss. As you learn more about TCP and UDP, you'll learn that UDP is a connectionless protocol. Essentially, it just sends out data. Our control systems usually don't require verification of commands, as such, our systems rely on UDP. The presentation layer, this is where the data is taken and formulated into viewable information. Oftentimes, this is when the raw BACnet IP data shifts into a viewable data format, whether it's an ASCII or Unicode. And then the application layer. Here, programs run to visually represent and physically interact with the data from the previous layers. Typically, building automation systems use applications built around HTTP or SNMP protocols. Additionally, applications can create FTP connections between one another to transfer data. That's pretty much the BACnet layering. So today we're going to look at MSTP over the RS-485 network. How is it built? What does it do? What does it talk? Before we do that, though, we're going to talk about a few fundamentals that I'd like to share with you. So we've looked at what is BACnet MSTP. So how does it communicate? BACnet MSTP, it means master-slave token passing. Token passing uses a mechanism to regulate communication on the network. The token is a special message that allows devices to gain access to the network for transmitting their data. Devices take turns passing the token to ensure orderly communication. You have a device ID. The master device assigns a unique device ID to each device on the network. The device ID typically ranges from 0 to 127. That's called 7-bit addressing. It can also go 0 to 255, which is called 8-bit addressing. This specific addressing scheme depends on the implementation and addressing mode chosen during the network configuration. Once the device IDs are assigned, devices can communicate with each other using BACnet services. BACnet defines a set of services for reading and writing data, controlling devices, and exchanging information on the network. So to communicate with a specific device, other devices on the network include the device ID in their message. This allows a receiving device to identify the intended recipient and process the message accordingly. And I want to go back to our drawing here and show you what I'm talking about. If you look here, this could be the supervisory device or a router. The token includes the device ID's address. So let's say the supervisory device wants to tell controller, ask controller 3 a question. Hey, what's the outside air temperature? So it'll send the token with the device ID in series down the line, but these are physically wired in parallel. So it's going to go to the first controller. First controller is going to say, well, this isn't addressed to me. I'm going to send it on. So it'll go to the next controller, and the next controller will say, it's not addressed to me. I'm going to send that on. Finally, it reaches the third controller whose address it's addressed to. Third controller says, oh, this is from the supervisor. He wants to know what the outside air temperature is. So here's where the token comes into play. The token gives the controller permission to respond on the network. Controllers aren't going to automatically chat their little minds off on the network. They have to have permission to talk. So that's what the token does. Gives that controller permission to respond with the query, with the answer to the query. So the query is, what's the outside air temperature? Controller 3 says, oh, it looks like it's 72 degrees. So it sends that back down the bus to the supervisory device. That's pretty much what that does. So one of the big qualities of BACnet is it has services and objects. So let's look at services. A service is a means or an interface between two devices to access and process information. It's a request to perform an action or inform the devices that some event has taken place. These are used for discovering devices and objects and for sharing data. Services refer to the appropriate BACnet guide of the device used to verify which services are supported. The following are some of the important services. Here we have object discovery. Object discovery includes the BACnet network asking who is, and the controllers answering I am. The supervisory device saying who has, and the controllers answering I have. These are device and object discoveries. Data sharing includes, let's say the supervisory device wants to ask a single controller, I need information like we just talked about, what's the outside air temperature? So it's a single query that's sent out and a single answer sent back. The read property multiple is another data sharing model. And what the read property multiple does is it sends out a single broadcast, but it goes to many controllers to collect many bits of information. So all the other controllers who have that information that's being sought will answer back. That's what read property multiple does. Write property data sharing is similar to the read property, except now the supervisory device or maybe another device needs to tell another controller, put this value in your numeric. We're changing the set point for the room temperature. So that's a write property. So the supervisory device may send that command to a single controller, and that's write property data sharing. Write property multiple is similar to read property multiple. Write property multiple will send a single command to many devices saying, oh, we're going to change our set points all across the building, so I'm going to send this information to all my controllers. That's a write property multiple. And then finally, we have things like subscribe COV and subscribe COV property, confirmed COV notification, and unconfirmed COV notification. So now we get into what are objects, because this is part of the BACnet modeling, and it does apply to BACnet MSTP, BACnet IP, Ethernet, things like that. So an object, along with its properties, describe the current status of the device or other devices on the network. Objects enable reading, writing, and performing the desired functions of the device. So here's the thing about objects. If it's a physical device, it's an object. But not all objects are physical devices. For example, if I have a temperature sensor made by brand X, inside that temperature sensor is going to be what is the name of the object, what's the address of the object, what is the description of the object, what is its current value. So here's some objects that BACnet works with. And this is not a comprehensive list, it's just an introductory list. So we have analog input and analog output. Those are actual physical objects. An analog input exists, you can touch it. An analog output exists, it sends a command to a physical object. Analog value is a virtual object, but it exists, it's an object. Then you have binary inputs, binary outputs, binary values, multi-state inputs, multi-state outputs, and multi-state values. The device itself is a BACnet object. Like I said earlier, all devices on a BACnet network are objects, but not all objects are devices. In this case, the device has its own unique object identifier, which contains the information of who am I, what is my current state, what is my current value, what is my name, things like that. Trends and histories and scheduling are also objects in the BACnet system. So things we have to think about when we lay out the MSTP network. They include the number and the types of devices, the physical layout of the building, and the data needs of the system and the desired balance between cost and performance. So here's an example of a building. Now, on the left side of this diagram, everything is BACnet over IP, but right here, we have these routers that convert the signal from BACnet over IP to BACnet over MSTP. The number of devices that can be on each network is limited. You can have up to 32 or maybe 33 devices on the network. The maximum length of a BACnet MSTP bus run is 4,000 feet. After 4,000 feet, you need a repeater. But the number of devices that you can put on the MSTP network is typically 32 devices. So you have to know what you're installing, where you're installing it, and why you're installing it. But basically, this is what it looks like when you have a distribution over a 4-story building. After the repeater, you have your MSTP devices. Each one of these has a unique identifier and a unique MAC address. So what are some advantages of MSTP? First off, we have the cost effectiveness of MSTP. MSTP networks are generally more cost effective than other BACnet networks. They use twisted pair wiring, which is less expensive than other cables that are used in building automation systems. Interoperability. You're going to hear this word a lot in the BACnet world. Interoperability is part of the BACnet protocol of MSTP, and it supports a high level of interoperability. Now, what this means is it allows devices from different manufacturers to communicate and work together seamlessly, provided they adhere to the BACnet standards. And you can actually go to BACnet.org and read the standards. It's very detailed, and ASHRAE 135 also covers BACnet requirements. MSTP is widely supported across various manufacturers of building automation systems. This means that a wide variety of devices and systems can be integrated using BACnet over MSTP. You can have a 4,000-foot cable run. MSTP can support a long cable run without a repeater. Once you pass 4,000 feet, or really a good rule of thumb is as you approach 4,000 feet and you know you're going to be adding more network, consider putting a repeater in so you can extend that network. But MSTP is definitely expandable up to a point. So you can support many devices on an MSTP network, and it has the ability to handle a reasonable number of devices per segment. And like I said earlier, you can have roughly 32 devices in a single segment. MSTP is a very simple network, and it's simpler to design and implement, particularly in smaller systems compared to other network options. Now, the thing about MSTP is you can have several buildings, and each building can have MSTP in it. And let's say you want to add a wing to one of the buildings, you can put a router in and expand that network on out. That way, you can continue to expand your MSTP network. MSTP isn't necessarily used to connect several buildings on a large campus, but MSTP is an excellent choice for small applications to medium-sized applications. It doesn't require expensive cabling. The cabling is two-pair twisted with shield, and it's a very efficient network. So one thing we want to look at is what are the limitations of BACnet? BACnet MSTP networks generally have slower data transmission rates compared to other BACnet networks. This can be a limitation for applications requiring high-speed data transmissions. The larger the network, the more complex it gets. And complexity, the more complex it gets, the more opportunities for failure. You want to reduce as many things as you can to a single point of failure where it's possible. Where it's not possible, you want to have redundancy. So MSTP networks can be simpler to set up for smaller systems, and they can become complex and difficult to manage when scaling up to larger networks with many more devices than you planned on. The token passing mechanism used by MSTP requires proper setup and management. If a device fails to pass the token correctly, it can disrupt the communication on the entire network. So if you lose one, you can actually interrupt the whole network. One thing a lot of people are looking at nowadays is the level of security required to maintain a network. MSTP, as far as my knowledge goes, the BACnet protocol, including MSTP, doesn't include built-in security features. This can make them vulnerable to cyber attacks, but MSTP is not by itself prone to cyber attack, but your system, if it's connected to the world, can be. So really, it's an IP issue, not necessarily an MSTP issue. One thing is true about MSTP is its need for a specific type of wiring. BACnet MSTP requires twisted pair wiring, which may not be present in older buildings. This could potentially add to the cost and complexity of retrofitting these buildings with a BACnet MSTP system. One really big thing is you can get a lot of noise interference on a BACnet MSTP system. If you put the BACnet cable near an electrical source, for example, it can pick up the collapsing field around a transformer. It can pick up the collapsing field around an electrical wire. Even with it shielded, sometimes you can get electrical interference if it's run too close to an electrical source. If it's not shielded properly, it'll become an antenna. And when it becomes an antenna, you lose data, you drop things. Another weakness in the MSTP network is that it could be going along and suddenly you could lose a controller, and in some brands, when the controller drops, so does communication. Or if it's not wired properly, you can lose signal from the point it's not wired properly on. So there are some issues with BACnet MSTP that you have to be aware of. Now, we talked about interoperability a moment ago. This is a hallmark word for the BACnet protocol. Interoperability. Um, and I'm going to give you a little war story here, if you don't mind. Back in the 90s, when BACnet was really starting to take hold, and people were really starting to pay attention to BACnet and its use, and start thinking about using it, a lot of manufacturers came out with the statement, "Well, I'm BACnet capable. I can do BACnet." Well, that wasn't necessarily true. In the 90s, a lot of people claimed they were BACnet capable, but didn't necessarily include all the things that BACnet requires for it to communicate seamlessly on a BACnet network. So interoperability in BACnet refers to the ability of a system and devices in that system from different manufacturers to communicate and work together effectively within a building automation system. Interoperability is a big deal. If I have manufacturer A over here, manufacturer B over here, and they can't talk, one of them is not BACnet compliant, or it's just been set up wrong. But if it's not BACnet compliant, you need to find an object that is BACnet compliant. Now, since the 90s, especially throughout the 2000s, the BACnet industry really got serious about, we need interoperability to work. We need everybody to be on the same page. If you say you're BACnet compliant, several things have to be true. And we looked earlier at the things that have to be true: the who is, I am, who has, I have, device discovery, device communication, being able to share information back and forth through token passing, things like that. So here's some considerations about how interoperability happens. BACnet is an open protocol standard and is developed to encourage device interoperability from different manufacturers. BACnet MSTP, as a part of the standard, follows this principle. Any manufacturer can design their device to comply with BACnet standards. Standardize objects and services. Now, we looked at objects and services just a moment ago, and what that means, much the beginning, let me put this back up here. This is pretty much the beginning of understanding how MSTP works and what it does and how it communicates. So what we're going to be doing next is looking at addressing. And in order to get to addressing, I'm going to skip a few steps here. Let me close this, close that, and close this. I'm going to show you. Now, the slides that I'm showing you come from some of our courses. What I've done is I've mixed several of our BACnet courses together to do this broadcast. And here we go. So we looked at, earlier, we looked at the different objects and we looked at services. Now I'm going to talk about baud rate on MSTP. MSTP is considered a slower network because its communication runs at slower speeds than BACnet over IP. Baud rate is the rate at which data is communicated to the devices. You can configure the MSTP networks to communicate at the following rates: 9600 bits per second, 19,200 bits per second, 38,400 bits per second, 76,800 bits per second. There's also a feature called auto detect. And I'm going to tell you, you got to use caution when you set your system up to use auto detect. All the devices on that MSTP segment must be at the same baud rate. And I'm going to give you an example. I had a client that had several buildings, had 5 JACEs. Each JACE had a minimum of 1 MSTP network. Most of them had 2 or more. And they all had a brand that used Autobaud. So what happened was, one day, a beginning BAS person went out to this job site and wanted to talk to part of the network, part of the MSTP network. And he plugged in his little communication device, but didn't find out what the baud rate was. He could have gone to the JACE and looked it up and said, oh, the baud rate is 38 for. So he could have done that, but he didn't. So what he did do was plug his uh, portable BACnet router into this network. And because everything was auto-bauded and auto-detect, the baud rate changed when he plugged it in, and it no longer communicated with the rest of the building. Auto detect is a very useful tool if everything's going to be all of the same page, if everything's going to be talking at the same rate. But if you have autobaud set up and you do anything to interfere with that baud rate and reset the baud rates, you've got a long day ahead of you, because now you're going to go back through the network and reset the baud rate. So auto detect is a feature that's available on a lot of controllers, but I just want to warn you, if you have auto detect set up and autobaud set up, then when you plug into that network, make sure that the device you plug into the network with is set up to communicate at that baud rate in advance. Otherwise, you're going to reset the baud rate, and you've got to reset all the baud rates and all the devices on that network until everybody's talking again. So the TP part of the BACnet MSTP. TP stands for token passing. BACnet MSTP uses a token passing mechanism in its message packet to regulate communication on the network. The token is a special message that allows the device to gain access to the network for transmitting their data. Devices take turns passing the token to ensure orderly communication. And remember what I said earlier, a controller is not allowed to talk on the network. I need to put a parenthesis right here. There's a lot of discussion going on about the language being used for MSTP, master slave token passing. Back in the good old days when I was a puppy, we all understood that what we now call the supervisory device would be the master device. And its children, the guys downstream from it that's connected to the COM port, the MSTP COM port, were called the slaves because they took the orders and obeyed the orders. They didn't give the orders. And that's where the token came in. I know that Modbus recently released a statement saying they will no longer use the master slave language, that they're going to client server. LAN has gone to client server too. I do know that BACnet is looking into it, but they haven't made an announcement about it yet, but an announcement should be coming. In the meantime, master slave only means that you have a device that's in charge, and all the devices that are connected to that device listen to that device and take orders from that device and do what that device says, and answers the device when it asks a question. So that's what the token does. The token passing mechanism goes to a device and gives that device permission to read the query and respond to the query. We showed you a moment ago where the supervisory device wanted to know from controller number 3, what's the outside air temperature. So it sends a token downline with the address of that device with the query attached. And it has what's called a checksum at the end of it to verify. It's a code that's built, and we'll talk about checksum here in a second. It's a code that's built that both devices use to verify that the message is legitimate. So that's what the token does. It goes downstream, and it gives the device it's querying permission to communicate on the network. That's what the token does. Device ID assignments. The master device assigns unique device ID to each device on the network. The device ID typically ranges from 0 to 127, and that's called a 7-bit address, or 0 to 255, that's called an 8-bit addressing. I'm going to address this shortly in just a moment. The specific addressing scheme depends on the implementation and the addressing mode chosen while the network was being designed. Typically, the 0 to 127 are other masters. And when you look at it, set up a JACE, for example, you'll see a section in the JSON of the BACnet network module that says what are your max masters, and its default is 127. 0 to 255 is typically the children under the separate masters. And that's typically how that was intended to go. Once the device IDs are assigned, devices can communicate with each other using the BACnet services. We read about the services a moment ago. Who is, I am, who has, I have. BACnet defines a set of services for reading and writing data, controlling devices, and exchanging information on the network. So you have to have a device ID, and that's the only way the device is going to know who's talking to it. He'll see the token, but if the query is not addressed to that device using that ID, the device isn't going to respond. So to communicate with a specific device, other devices on the network include the destination device ID in their message. That's included with a token. This allows the receiving device to identify the intended recipient and process the message accordingly. So the device ID object identifier is used in a BACnet network as a unique identifier of a specific device. The device ID must be unique on the entire BACnet network. Every manufacturer has a BACnet assigned vendor ID, and if you want to know what that is, if you want to see a complete listing of all assigned vendor IDs, you can go to this website. I'm going to save you a step though, and I'm going to share the screen I'm using that has the list of vendor IDs. It's loading now, and here it is. I don't know if you can see it very well, but this is from the BACnet committee. These are assigned vendor IDs for everybody who's registered with BACnet, who've had their equipment tested, who are BACnet compliant. 0 is ASHRAE itself, and ASHRAE is the industry standard for defining BACnet 130. ASHRAE 135 defines how BACnet operates. Vendor ID 1 is the National Institute of Standards. ID 2 is the Train Corporation. 3 is McQuain. 4 is McQuay. 4 is PolarSoft. So it goes on. Johnson Controls 5. ABB is 6. It goes on down, and there are just thousands of vendor identifications. So why am I showing you this? If you follow the BACnet standard, you're going to use the unique vendor ID for the brand that you're installing. So here we go. Every device being added to the MSTP network has a unique MAC address. The device ID is derived via a combination of the vendor ID that I just showed you the list, times 1,000, plus the MAC address. That is the recommended standard. I'm going to be honest with you, as an experienced field tech, I don't see it followed that often. It really should be. And when you're establishing your standards, if you're installing, for example, I don't know, pick one, Johnson Controls. Know what the Johnson Control vendor ID is. If let's say you're installing Siemens, or let's say you're installing Dissects, know what your vendor ID for that is, so you can build MAC address. You can build the device ID based on the BACnet standard. So here's an example of one. Let's say my device has a MAC address of 3 and my vendor ID is 364. I multiply 364 by 1,000, which gives me 364,000, and I add the MAC address. My default instance number for that device is 364,003. If I have a MAC address of 20, I go through the same steps and I end up with that MAC address right there. If I have a MAC address of 123, same principle. Multiply by 1,000, add the 123, I get my unique device ID. The device ID has to be there, and it's recommended by BACnet to follow this as the standard. So I talked about 7-bit and 8-bit a moment ago. BACnet MSTP networks, the device IDs are typically assigned to 7 or 8-bit values. The number of digits in the device ID depends on the chosen addressing mode during network configuration. 7-bit addressing mode, 0 from 127. The device IDs in this mode are represented by single decimal digits such as 0, 1, 2, etc. through 127. These are typically reserved for the masters that are in the network. 8-bit addressing is 0 to 255, like I said earlier, and these are the children under each master. These addresses should be used for the children. The number of digits used to represent the device ID doesn't affect the functionality or communication in the BACnet MSTP network. It primarily depends on the addressing mode chosen during the network configuration and the maximum number of devices expected in the network. Whether you use 7-bit or 8-bit addressing depends on who your engineer is designing it. This is based on the requirements and specs provided by the BACnet device manufacturer or the system integrator. It's dealer's choice. BACnet respectfully requests, please follow the standard. Now I want to talk about max master and bus devices. This is critical. And when I've gone out to rescue a lot of jobs, this is where I see a lot of mistakes. In a typical BACnet network, the network interface card used to access the MSTP bus is called the bus master. This is usually the head-end device, the JACE, the supervisory device. 4 configurations are required on the master device. Its baud rate must be assigned and it must be consistent with all the baud rates on the network. The MSTP address must be assigned. On the master, it's usually 0. Max master is the number of devices on the bus plus a little bit extra. And then you have max information frames, which we'll get into in a more advanced class later. So in order to increase network efficiency, we recommend configuring the max master of the highest Mac device. So let's say I have 15 devices. I'm going to set my max master to 17. That gives me room to grow. In case I add another device, it'll auto detect that device and assign it. Give yourself a little buffer space, but don't let it just sit at 127. Let's imagine that your JACE has 2 COM ports and that you have running 2 MSTP networks. If you don't, and let's say you only have 10 devices on each network. If you don't change your max masters, the JACE is going to sit there and poll and keep looking for everything beyond what you've actually got. It's going to poll all the way out to 127 and then start over. That's how serial communication works. That's how MSTP works. It starts at 0 and goes to 1, goes to 2, goes all the way out to 127. So if you want to improve the efficiency of your MSTP network, set your max master in the JACE just a little bit more than the actual physical number of devices on the network. So that's what I'm getting at here. When you have less than 127 devices, 127 is the default. The max master prevents the poll from master from exceeding the current value set. There's a feature called the poll from master. That's when the master goes out and looks down the network and says, I see here I'm supposed to have 127. I'm going to query 127 devices, even if they don't exist. Keep that in mind. You're going to need to know that later. 32 devices with MAC addresses ranging from 132 on your network. A max master of 33 ensures that the poll from master are not done for addresses higher than 33. That's the whole point I'm getting at. The default value is 127. Get rid of that and put in the actual number of devices plus a margin for buffer, because the next guy that comes along isn't necessarily going to look at his max master assignments and just slap a new device on there and hope the network picks it up. So leave the next guy a little buffer space. If a new device is entered outside the value of the max master, the network will not see the device until the max masters have been changed to include the new device. That's why you give yourself a buffer space. I'm going to skip dip switch addressing. And we just talked about how to optimize your MAC address and max master. If you have 33 devices, make your max master 34. If you have 15 devices, make your max master 16 or 17. You can tune it a lot better when you keep the JACE or the supervisor from having to poll objects that don't exist. So if you're having trouble, verify that you've wired the polarity correctly. And we'll get into that in just a second when we deal with wiring. I'm going to close this up with wiring. RS-485 achieves binary transmission by switching the voltage polarity between the transmit and receive side. And I'll show you that in just a moment. If the receive light is on when there's no communication, there's a good chance that the polarity has been reversed. I've seen this a bunch. I've seen polarity get reversed. I've seen somebody comes along and adds a new one and doesn't really understand BACnet. He'll swap the leads from transmit to receive to transmit. That shuts down communication from that device all the way out. You end up with inefficient communication up to that device. You can really screw things up if you don't wire it right. You ensure that all devices have a unique MAC address in a device instance. No two devices should have the same number. If they do, they will quit talking to the network to each other and you'll have communication problems. Ensure that all software device instances are unique on the network. We just covered that. Validate the baud rate is the same for all devices, including the repeaters. Check if there are more than 2 end-of-line terminations present on the same segment. No intermediate device should have an end-of-line terminator. We'll get into that in just a second. If there are third-party devices in the network, remove them. If they cause problems, put them on a different segment. In order to help narrow down a communication issue, divide the network in half and verify if the devices on that half are online. Repeat this operation until the network is functional. So you start with the whole network, divide it in half, see if communication picks up. If it does, then the problem's on the half you excluded. Re-include it, divide that in half, and keep dividing until you find the device that's offline. And you can swap working and non-working devices as long as you follow the proper addressing. If you do end up doing this, then you have something else going on. You may have a wiring configuration problem or an addressing problem. So we're going to now look at BACnet MSTP wiring, and I'm going to pull that up real quick. Let's see. I'm going to close this guy and close that guy. Bear with me. I'm going to pull up the information on MSTP wiring. And here we go. So MSTP wiring protocol uses the EIA 45 physical layer. We looked at the BACnet layering topology a moment ago. BACnet MSTP uses what's called the BUS topology. Communication wiring must be installed on a daisy chain format when you're using MSTP. This first thing right here, that is not a BUS topology. That's a star topology. This next one is not a BUS topology. That's called a T-tap topology. And this next one is the BUS topology. I know it looks like the letter W, but it's literally daisy chained in parallel, going from one device to the next device to the next device on like that. So BUS topology, daisy chain configuration means that there's only one main cable and every network device is connected in parallel directly along its path. It's important to keep the same color coding for transmit and receive. Transmit should be one color and receive should be another color. I've worked with enough building automation companies to know that no two building automation companies necessarily use the same color coding. Some companies use white for positive and black for negative. Some companies use black for positive and white for negative. BACnet recommends red for transmit, black for receive. So here we have a shielded cable right here, and we go back to this wiring diagram that we looked at earlier, and you see there's a transmit side, and it's represented by the red wire, and it's just series connected to the next controller, to the next controller, and to the next controller. Same with the black wire. It's connected to the next controller, to the next controller. This is a parallel wiring. It's a series communication bus. The shield is grounded on one end, not the other end. See, right here it's grounded, on the other end it's not. So here's a few tips for wiring a BACnet network, MSTP network. Avoid unwinding the twist of cable when not necessary. Twisting the insulated conductors around each other reduces outward noise and improves immunity to external noise picked up. We talked about earlier to avoid electrical cables, to avoid vibration, to avoid crushing or overly bending. We don't want to do any of those. The nice thing about leaving the cable twisted as far up as you can, up to the termination point, means that the cable has less of a chance of picking up interference. I once rescued an installation at a military base in Missouri where the person who had installed the network had untwisted it at the panduit, and he had about 3 inches of wire going up to the controller. That 3 inches became an antenna, and it took me forever to figure that out. But I finally figured it out. I retwisted it, re-terminated everything. I had to go through the whole campus and do that. It eliminated a lot of the noise that was being picked up. It was near an electronic warfare portion of the military base. Avoid using too much bare wire so that adjacent wires don't short when connected to the controller. I've seen this plenty of times where when you strip the wire, if you strip more than what's absolutely necessary to go into the terminal block, sometimes you get a little dingleberry piece of wire sticking out, and it'll touch the wire next to it and short it out. You lose communication. So you want to avoid stripping too much wire off because you can accidentally get one of the strands touching. Don't use solid wire, by the way, on MSTP. That's just stupid. Don't use solid wire. Use stranded wire. Make sure when you strip it, you twist the ends of it thoroughly. Make sure the unstripped portion is twisted also. If you have a transmit wire coming up into the positive terminal and you have another transmit wire leaving, when you get ready to land those two, twist them together. Twist them together. You reduce capacitance, you reduce impedance, you improve the electron flow. It makes for just a cleaner connection. This is a standard that should be observed. Avoid running network cables near a DC signal switch or a variable frequency drive or power lines. These are all common sources of induced noise. Secure the network cables to reduce vibration as much as possible. Don't use T-taps or pigtails on the network. Controllers may drop out of the token pass or pass packets that may be lost. I'll show you an illustration of a T-tap. Here's the right way to bus, and I want to thank Neptronic for this illustration. I got permission to use this. They do great illustrations. So here's the supervisory device, and the BACnet communication leaves the supervisory device, goes from one controller to the next controller. Here's a device down here, then it goes back up to another controller, drops down. This parallel run stays. This is going to sound so confusing. It's series, one after the next after the next. The wrong way to bus is when you include T-taps, and I promise you I've seen this a million times. A lot of people who don't understand BACnet MSTP assume, hey, I'm putting a VAV box here in this zone. I'll just slap the controller in, run my BACnet MSTP wire. There's a controller over there. I'll just land it at its communication port. That's called a T-tap. That's a no-no. You'll lose communication. Stop it. Don't do it. If you're having communication problems, look for T-taps. You don't want T-taps. There's one right there. Here's another one. Here's another one. Don't do that. I can't emphasize this enough. I spent a great deal of time at a very large, internationally known manufacturer of military equipment. They were having terrible communication problems. I got out there, and one of the things I found was T-taps everywhere. I cleared those up. It didn't clear up the problem, and I'll tell you why in a minute. But the biggest problem I found was all these T-taps. Don't do that. Shielding. I want to show you something. See right there where that red circle appeared? That's earth-grounded shielding. It's grounded on one end only. It is not grounded on the other end. Do not ground the other end. You ground one end or the other end, but not both ends. The preferred method is grounded at the supervisory panel where it begins. If you ground both ends, you've made an antenna. This is another one of the things I found at that very large manufacturing plant in the Midwest. Shielding grounded at both ends. That's a no-no. So that's bad shielding to ground it at both ends. See, this is an example of bad shielding. Just don't do that. You're going to make an antenna. You'll really mess things up. So We're going to talk about end-of-line terminations and look at this picture of the mirror. Have you ever been in a fun house or had two mirrors face each other and you can see this infinite progression of mirrors? That's pretty much what happens on a BACnet MSTP network. It sends a signal to one end and it comes back, sends it out, it comes back, sends it out, it comes back. And that's kind of called bouncing, or you get a cascading noise or something like that. In order to avoid reflection issues, use end-of-line terminators. They must be installed at both ends on a physical network wire. Communication is achieved by using electrical pulse signal. When no end-of-lines are installed, the pulse signal reflects backward and collides with other data pulses. The resistor absorbs the pulse energy and dissipates it as heat. So at the very end of the run, if you look at this example here, at the very end of the run, put an end-of-line terminator. Different brands call for different ohms. Look up the brand that you're installing and find out what it requires for the end-of-line termination. Not all brands are the same. 120 ohms is typical, but I worked on a brand that was called for 249.5, 250 ohm end-of-line terminators. Know your manufacturer's data. So here's how that looks. Let's say you have a transmitter and it sends a pulse down to the other end. And because you have this, in this case, 120 ohm end-of-line resistor, the data pulses go just one way and it doesn't bounce back up the cable. If you don't include end-of-line terminations, the transmission goes down one end. Without the end-of-line terminator, it's going to bounce back out and interrupt data communication. Here's a little picture of a data packet falling over in the other data packets. You don't want to do that. So we looked at MSTP wiring, bus topology. We've talked about wiring tips, the right way to bus, the wrong way to bus, how to shield, how to not shield, and what end-of-line terminators look like. And overall, in this entire presentation, we looked at BACnet MSTP. We looked at the standards that are involved from BACnet. We looked at why it's important to follow the standards. We looked at the importance of interoperability, which is a huge deal in the BACnet world. Be interoperable. Make sure that the equipment you pick, if they're two different brands, that they're both BACnet certified. If they're not both BACnet certified, you may have communication problems on the network. We looked at addressing, how every device must have its own unique address. We looked at how token passing starts at the beginning of the message, includes the address, includes the query, and at the end of the message is a thing called a checksum. It's a binary code, usually ones and zeros. Each controller, if it's BACnet certified, has an algorithm generating algorithm. It has an algorithm in it, and it generates what's called a CRC. It's an error correction code. If the codes match, then the communication is valid. If the codes don't match, the communication is probably corrupt. So you have the token. The token gives the controller permission to talk on the network. The controller then supplies information that the original message called for. So that's token passing. Let's see what else. We looked at end-of-line termination. We looked at MSTP addressing. We looked at how our addresses derived. BACnet calls for, BACnet has a standard. Use the vendor ID, multiply that by 1,000, then use the MAC address of that device, and you will have your device ID. That is the standard that BACnet requests you use. I can tell you from experience, hardly anyone follows that. It's best to follow it. That way, the next guy that comes along, if he's never seen your installation, but he's a guy that has to troubleshoot why it's not talking, can come along and can see by the addressing what's going on. It's important to use consecutive addresses. It's important to use the right baud rate, and it's especially important if you use auto baud to label the crap out of everything, because you want the next guy to know what baud rate everything's talking on. Put that somewhere in the panel. This network number 1, it's on baud rate X. Network number 2, it's on baud rate X. That way, when the guy plugs in his little portable router, he's going to auto baud and change the baud rate of all the devices on the network and kill the network. I've seen that happen. Basically, that's BACnet MSTP in a nutshell. I really hope you've enjoyed this high-level presentation. It's a high-level look at what BACnet MSTP is, how it works. 60% of all buildings are BACnet. Over half of those are BACnet MSTP. When you go out on troubleshooting calls, it'll be important for you to remember, has polarity been observed? Has proper addressing been observed? Has shield grounding, and I got to tell you, shield grounding is a huge issue. Ground it properly. Have they put end-of-line terminators at both ends of a network? You don't put an end-of-line terminator in the middle of the segment. You put it at both ends of a segment. That's very important to remember. So when you're troubleshooting and it's not communicating, look for those things. Proper addressing, proper end-of-line termination, make sure the polarity has been observed all the way down the segment. I mentioned addressing. So this has been a presentation by Smart Buildings Academy. If you want to know more, contact somebody at Smart Buildings Academy. We have all kinds of courses. We've seen people come in not knowing anything about building automation systems and leave after 6 weeks ready to be in the field by themselves. Give it a thought, give it a try, and thank you for joining me for this presentation. I'll see you in the future. Have a good day.